for you to and for you, Paige, to invite us to present. I'm glad that we've finally managed to make this happen. We have a pretty broad effort in climate and sustainability within IBM Research. So IBM Research has, I think, around 2,000 people across 7 research labs. So it's a pretty big organization. And focused on kind of geospatial for climate and sustainability. There's a handful or more of us across a few different labs focused on that. And so you'll hear a bit about it today. There's, I think, sort of 3 main areas that we think about it. First is on the computational system side, which Johannes will really be talking about today. So this is sort of geospatial analytics. The other is on AI algorithm kind of approaches. And so we're doing work at the moment with NASA focused on big AI foundation models, which is a really fun growing area. And then the third is obviously applications, which and so things like above ground biomass and methane detection and climate risk and impacts and so forth. So that's just to give you a bit of an overview of what our focus is. But for this, we're kind of focused on actually showing you something that is, hopefully useful and constructive for you all. So I'll pass it to Johannes. Thanks.
Thanks, Campbell. Let me share my screen. All right. So thanks so much for giving us time to present here. Okay, that's appreciated. I hope you can see the right screen by now, not the one I meant to share. Let's try this again. We are sharing. All right, good. Let's try to show the correct screen. Sorry, give me a second. I'm sharing the wrong screen.
We saw it first up.
Okay, good. Then you saw my emails. Very good. Always got the right thing to share. All right. So I hope you can see my screen. There's a PowerPoint up. All right. So yeah. Let me make a second attempt here. So first of all, thanks again for letting us, present, for letting us be here. Let me also say one thing. Please, at any time interrupt questions or comments. This can be very interactive. As Campbell said, we're not trying to talk about everything we do, and we're more like trying to talk about one thing which we find particularly interesting, which we're working on. One among many. Also, let me say I have a very hard cut off at 12:30, unfortunately. So if I suddenly just run away, just please email me, etc. All right. So with that said, let's jump into the matter. So as Campbell said, we're going to primarily talk about geospatial computation today, which has actually some history in IBM. Okay, so there was actually back in the days in 2014 a project started back then called IBM Pairs. Obviously 2014, this is, shockingly almost 10 years ago. The world of what was available in geospatial, especially geospatial open source at scale, was much different. Now, so the idea with Pairs basically was, let's use the whole H-based MapReduce, Hadoop stack that basically exists for geospatial. So what you see here, basically what happened back then, there was an underlying HDFS storage layer. On top of this, there was data stored in H-base, which is actually really interesting because this is it's somewhat similar to what people do with ZAR these days, So what we do in HBase is, raster data is chunked into sort of chunks and then aligned in time. And now people are chunking raster data again in ZAR to get similar performance, So that's kind of nice. So things sort of, reappear. There was also Postgres storage here for vector storage. Then on top of this, there's a compute layer, obviously, back 2014, if you're in the HBase world, you had this Hadoop for MapReduce, which is really powerful, but obviously somewhat painful to write code for anybody who ever tried to write, Hadoop code. Metadata storage, APIs, and on top of this, there was an SDK, again, simply, because in 2014, we wrote our own SDK. These days people say, hey, we hate proprietary SDKs, but in 2014, there wasn't that much there. There was open source, okay. And they were successful, successful in multiple ways. This grew back then into an asset that had 120 nodes in a cluster. We ingested terabytes of data every day. There was something 10 petabytes of data in the storage. Was then used for many downstream applications. And then, if you're in a corporation, obviously the nicest thing that can happen to you is stuff becomes a product. That's sort of you don't publish paper, you publish papers as well, to go to conferences, but obviously you're trying to drive product, even in a research organization. So this became sort of a core part of what is known as the environmental intelligence suite, okay? But now, fast forward, 9, 10 years, and, lots of these things are obviously not modern anymore. If you start a project like this these years, you would never start saying, hey, let's put raster data on Hadoop, because there is other frameworks out there. So a big thing of what we've done in the last 2 years is we've modernized this from a technology point of view, okay? Which is funny because if you have a running asset that runs on 110 nodes, It's sort of like, trying to, build a train while the train is running at 80 miles an hour. So it's a very special experience. Sometimes people say, oh, just make the architecture chart, but getting from here to there is not quite the same thing as just making the chart. Okay, but you see now here, and there's several things I want to point out, which have changed a lot. The first thing is, Pairs was like a monolithic thing. There was one big giant data mountain, in the early 2010s, you'd say like all the data is going to be there and everybody's going to use the stuff that is there. And this is just not happening anymore, And at the same time, also like not everything just, it's not a contentious thing, not necessarily everything is just going to necessarily only be in cloud, okay? Some people have like governance constraints. They want to have this like on-prem things for, governance reasons. Even if it's in cloud, it might not be in the same region if you really have like very large data. Federation is becoming a big topic, I think, for you guys as well. How do you federate between different instances? If half your spatial data is here, half is there, half is there. How do you do stuff quickly? That is one big thing. But then, and because of this, driven by this, we've actually started deploying this thing at a bunch of partners. So this runs now in cloud, it runs on IBM on-prem, this runs at partners of IBM on-prem or in their clouds, which is why you see here there's options for storage. We've running this on GPFS, on HDFS, on NFS and Lustre. For cloud, this runs on Object Store. Then at the storage layer, we still have HBase in here. We're looking more and more into ZAR to see like, what the performance pros and cons are. This is something that is interesting. In HBase, you get a bunch of things for free you don't get with ZAR, sort of restructuring of the data on the fly, etc. But that doesn't mean that, I think in the long run, at some point, we're going to abandon HBase as a spec. This is sort of just open source usually takes over. There's no part competing again. And then you see like Dust, Xarea, etc. on top of this. I don't want to go too much into this. The main thing I want to talk about, you might say, what on earth is this? All right. That's actually the thing I want to talk about. Okay. So what on earth is this? This is like one of the second big things we sort of, doing apart from the federation story, and sort of going away from this monolithic, big, IBM owned data mountain. The thing is, even if you, federate, and even if you have like great storage, etc., in many like sort of these like geospatial applications, you tend to like search through data. Lots of questions are, I have like, lots of ERA5 data. I need to find the extreme precipitation events, or I have like all the CMAP6 data. When does it get really hot or something like this, And you can even still write papers, where people say like, I find like, the extremes in CMAP6 and then I like make the statistics and sort of do something about this. And it's remarkably often that this is like table scans, You like load the data, you subset it, you put it into memory and just like search through the data, etc. Okay. And so there's the question whether you can do something better, than just sort of like accessing native data, and you see this obviously, but you see here just to say, usually like a database where you say, can I do something better? You talk about building indices, this is effectively what we do. We're just calling it slightly differently, In a way, people doing some things like this already with catalogs like STAC. Like in STAC, you would basically see, oh, this tile of Sentinel-2 has like 10% cloud. This tile has like 55% cloud. But if you not care about clouds, if you care about NDVI, you're screwed, okay? Then you have to load the tile again, compute the NDVI for the tile, and look again somewhere else, okay? So for lots of applications where you're like searching for something, you actually have to read the raw data to then decide whether you need the data. And this is something we're trying to find out, what are different tools to actually identify data you need before you've loaded it, This is obviously relevant for federation because, if I can identify sooner what I need, I can decide sooner what I need, but even for other use cases, if I just don't have to load everything, I do things much faster. So before I go into sort of some tech implementation, I'll tell you a few things in a second, what you actually do under the hood. Let me show you some results, okay? So here, there's a few things. The example here in this case, just to say we have a big footprint now also in sort of geospatial foundation models. So I'm going to frame this a bit into the life cycle of foundation models, but you can think about this also beyond foundation models. Just I want to find stuff in data. I want to discover things. I want to analyze things quickly. And somewhere between going to native data and just like speed stuck in a catalog, okay? For example, you might want to identify biases in training data. That's sort of obvious thing. If you do like pre-training at scale on foundation models, you train very large AI models, in an unsupervised setting. You worry if your foundation model, there's like some bias in the data, whatever that means, but then your model might have some bias, Similarly along those lines, you want to identify a sampling strategy, So if I say, if you pre-train a geospatial model, on all the Sentinel data for the US, do you really need all the Sentinel data for the US? Maybe if you just like use 10%, you get the same results just because it's a similar distribution. Similarly, if you just like sample all of the US, you heavily bias away from urban centers, because you're going to basically like a random sample of Sentinel for the US or some other high resolution satellites going to hit like a forest, going to hit like a field or something. You have to think about, if I pump lots of like satellite images through GPUs, what's the biases I'm putting in there, Similarly, when I go to this is the pre-training, we'll go to fine-tuning steps, I have to identify training targets, like typical things, in, let's say I want to build a model for floods or for land scars, for fire scars, I have to find all the incidents when it rained a lot, for like floods, and then maybe do a flood model there. And if I'm lucky, somebody else wrote a paper and there's a public data set out there, like all the floods in the United States or all the floods in Europe, and I'm really lucky. But if not, I have to often do this work, So often this show me where is really relevant for identifying labels, and then, if you think about also for inference, again, basically for run sort of a large AI model that, for example, does a flood mesh segmentation and image segmentation for flooding. If it didn't rain, I don't need to run the model. So again, I can sort of do things like this. So one example here is then you see in the top right, this is just from ERA5 data together with, I think, land use data, I think Cropscape, okay? So if you take ERA5 temperature data and look at different urban or different land use categories, in this case, urban or forest land use, you see there's different warming over the last, I don't know, 20 years. So this is for the US, So this is something, it's sort of a simple show me where. Effectively in the top right, the question is, get me all the ERA5 data for parts of the US where land use is urban or forest. For this data, I only care about the extremes, which is above 37 Celsius, and then count this up, and this is sort of a simple thing, but you might be interested in scientific purposes, but again, also because, it might be relevant for your sampling stuff, and with the stuff I'm going to show you in a slide or two, this is executed 20 times faster, okay? Then similarly, in the bottom right, you see a question. I say, all right, let's find all the heavy precip events near water bodies in 2021. So I want to find, again, in some climate data, some weather data, again, we use ERA5, all the events with more than 25 millimeter precipitation per hour, but only when there's actually land use in the area that is water, So this is a bit not super nice yet. It should probably be heavy rain within the watershed, but you sort of see where this is going, Often I want to sort of show me where, show me when, and this is going to be 75 times faster, okay? So you see, I can get heavy acceleration by, building sort of indices, and you'll see the technical details in a second, that live between the level of the raw data and just the catalog, okay? I would actually, in principle right now, I would tell you more about the technical, these examples here, but I think it's probably better if I jump to the technical details, okay, of what we're actually doing, okay? This probably makes more sense, and also looking at the time, because I want to show you a quick demo in the end. So effectively what we're doing is this, okay? So if you have, on the bottom level, you have the native data in some sort of grid, whatever it is, some projection, who knows what, then we're simply aggregating this data right now spatially, across, largish areas, we call these whatever, supercells or something like this. They can be 32 by 32 pixels or 64 by 64, something we find suitable. And then we basically calculate a bunch of statistics for this. Min, max, mean, standard def, also a sample, count, a bunch of quantiles. For categorical data, we compute histograms, and we persist this in Geopark, So then we have another layer, we actually have a partition size for Geopark, okay? So we built these Geopark files. They look something like this. There's a spatial key in there. Why? Because spatial keys are really, really nice for fast joins, There is no ambiguity about floating point coordinates or something like this, So if you have a bunch of things in spatial keys, with some sort of a fixed, algebraic index, you can do things really quickly. Also, the way we built this is built on nested grids, so these spatial keys are so somewhat effective if you go from different resolution levels to another. But if you want to join this with data that you're not happy with the spatial key, you sort of want to join this with something entirely generic. There's also, so it's Geopark, there's also a WKT in there. It's know what is the area this defines. Then for this area, time step, and then there's a whole bunch of statistics. That's really as simple as it is. There's no rocket science in here, but it's effectively defined an index. So you can see if I look for the heavy precip event, I can basically look at the precipitation data and see, all right, throw everything away where the minimum of precipitation, if I look for heavy precip events, throw everything away where the max is 0. I don't have to look at any of this, in the data. And so many things immediately fall away. And similar things like temperature extremes, etc., left and right. Similarly, if you look for land use, then we look here for these histograms categorically, Geopark is, of course, really nice. Actually, Geopark doesn't really matter here. Parquet is really nice because, we have to really look in the bottom left corner, but if you know a bit about how Parquet files are structured, Parquet files basically very, very suitable for predicate pushdown. Effectively, if you filter the data and subset it, you can really put this into the stage via, arrow, the loading stage. So these questions of, I only want the stuff for this area, for these spatial keys, for these amounts of precipitation, you can really like sort of push it into the Parky stuff. No, so effectively, although we have an underlying layer of native raster data, either stored in HBase or Corg or ZAR, we have on top of this data of coarse-grained data in Parky, which is then amenable to basically serve the sort of an index. It's much more finely grained than what we put into a stack, but it's much coarser. But it's obviously much coarser than having to go to native data and doing stuff. And this brings you sort of to some resolutions. Now, I can show you like a demo what this looks like in a second. Before I do this, let me pause for a second and see if there's questions or comments. Whether I should repeat something, whether anything is unclear, anything somebody would like to say.
Just as a heads up, we usually do keep questions to the end. So people are welcome to ask now, but we often will leave them to the end just so we have a cleaner recording.
Yeah, that's good. That's good. Just so you say, I mean, I have to drop, but then Campbell and Rome are going to be around, So then what I'm going to talk you through is this example, So this story here basically of accelerating, finding heavy precip events across like water bodies in the US, So this is again 2021, you have ERA5 data, you have something like 8,000 timestamps for the year, you have underlying land use data. In this case, we use Cropscape, which is a vastly different resolution. But Cropscape's a nice proxy for finding things because, although it's US Department of Agriculture, primarily for like corn and soybeans and, where cotton grows, it's pretty high grained, like finely grained, like land use data set of 30-meter resolution. One thing you're going to see is, while we're sort of good with the underlying technology, what we're not yet good with is the user experience. You'll see this in a second. So I'm going to show you like what this looks like in a notebook. But from the user experience point of view, this is definitely work in progress. Okay, just so you're aware of this. Okay, so but this is something I think for us for the next 3 months to think what the right user interactions around this are. All right. With this caveat being said, let's bring out the notebooks. So I'm going to talk through this somewhat quickly, as I said, because we really haven't like nailed the user experience part of this here. But I think you'll sort of see the most relevant things. So effectively, you'll see here, there's some libraries, some credentials, some are our libraries, some is like standard stuff out there. I effectively, identify the data I need, Cropscape and ERA5, in this case, just, we always use numeric IDs. There's lots of discussions whether IDs should be alphanumeric or numeric or names or not, this is like a long history we have, and I'm happy to, it doesn't really matter. Effectively here then quickly, we connect to these overview stores, said right now, because they're just Parky files, they can be stored whatever, that doesn't really matter, in principle, if we have GPFS there, if, in cloud, we put them just into like cloud object store, Then also one thing that doesn't really matter so much is we load from our AOI store Polygon for the US. Again, this has nothing to do with this like, overview story, this is just the ID, this defines the query area we need. And you see from the URL, this goes back to our technological legacy back to 2014. Then we still have the API URLs with like old product names in them. All right. So then the first thing we need to figure out now for the Cropscape data, I said, the overview data, is stored in Parky files, and basically there's some partitioning here. So basically for the query polygon I need, I find what are the Parky files that might be relevant to this area. And again, this is going to be all eventually be hidden from the user, but right now I find which Parky files I might care about. I get a bunch of Parky files. They have like, spatial keys that identify them, at a certain level. I do the same for ERA5. You see, obviously, ERA5 is much coarser data, so I need much less files. But you also see the spatial keys here are shorter. Effectively what happens is this is like a quad tree key. So this is like in base 4 numbers, you throw the last digit away, you just coarse-grained everything. Then the first thing we do is, and this is like where Parky now becomes nice. I forget about the benchmark here. I basically now load all the Cropscape data, where I find land use more than 0 for water areas. Okay, in Cropscape, water areas category 111. So this is an example of predicate pushdown here. This is just basically GeoPandas. There's not much geo in here though. GeoPandas runs PyArrow in the back, which then, basically goes to these Parky files, filters out all the rows I have, which have like, land use for water areas more than 0, and we're good, Then the second thing I do here is, because I say I have this hierarchical grid, I coarse grain, because Cropscape has much higher resolution than ERA5. I coarse grain everything up, simply happens by throwing away some digits from the key. So far, so good. Then the next thing is, all right, here's the fitting ERA5 data, So now I basically say I go through the Parky files for ERA5, and I do again 2 filters. Again, this is straight up predicate push down. I say maximum precipitation in this area should be above some threshold. And I want the spatial key to be actually something where I previously found land use water, okay? And again, you can make this more complicated by saying it shouldn't be exactly on top of each other, it should be nearby, or so you see where we're going with it, you know. But I hope the idea is clear that the nice thing is now we loaded only what we need. You know, now we're effectively done. Now what we're doing is we have at a course level, at this overview level, we have candidates where we might find these precipitation events. Now we go to the raw data. Now we reach out to HBase. We have a threshold here. You know, this is sort of what happens. You go to HBase. Effectively, what we do here, you could imagine we would just go to like a ZAR store here, or like to COG files. In our case, there is a separate sort of API that goes directly to HBase. Obviously, HBase has very nice random access qualities for fast access. But now we've read out basically where the data is, and we're done. Okay. So now you see the result here is a list of, I think, 150 events, lat long and timestamp. You know, we found from the native data, where Jennifer would plot it on a map, would give you exactly basically this. Okay. So you see, and I say 75 times faster, we actually measured this. We did like all the same thing, you know, without the overview dance, you know, but you see it's basically like a search and filter story, you know. But you see, we think, you know, we'd be interested in it. This is obviously like a very low level thing. Not everything can be done this way. You know, in other cases for search, you might be doing other things. You know, if you want to find, you know, a very complex pattern, you would not find it with something like this. You know, there's other things you might want to do then, which are more AI based, you know, but the idea is always filtering lots away of the data you don't care about, you know, when you search, you know. All right, that's everything I want to present. Questions, comments?